developers in the last, up until very recently, have had to understand not the physical processor, but they had to understand the notion of a process. There's the correctness side of, well, when I write this line of code, it is going to translate into the right assembly language down under the covers. I think this big transformation that we have going into the AI space, where we're now programming with natural language, that's not a formal language. You get to think about the logical process. We will ensure that we give you durability underneath that abstraction so that as the infrastructure is doing all sorts of chaotic, weird things, we will compensate for all those weird things. You just get to think about this logical process.
The idea of programming languages and just programming models has evolved over time. You have been deep in the weeds, studying it, being part of it, helping shape it. Tell me about what you see as like the evolutionary through line or thread that goes through it.
So I recently did an internal developer conference for one of our users, one of our customers. And the very first slide that I showed them was a slide of a processor. And I asked in the room, how many of you have programmed in assembly language? And there were about 50 people in the room. Surprisingly, half of them raised their hands.
Really?
I was like, wow, really? I thought I was the oldest one in the room, right? I did. And when I was in school, I programmed assembly. And then the second question was, how many of you still program in assembly? And unsurprisingly, no one raised their hands. And so nobody programs in assembly anymore because we came up with a higher level abstraction. There's still assembly language running. There's still program counters and instruction registers and memory, registers and all of those types of things. Those physical components are still there. But we have a different abstraction. And so that's the through line, is that we're always moving up the level of abstraction. But I'll tell you honestly that for the most part, the last, I would say, certainly the time that I've been doing this, which is more than 3 decades, sure, we moved from assembly language, and our languages got incrementally better and a little bit higher level in terms of abstraction. So C you had to do your own memory management. Then we had an abstraction that allowed you to not have to do your memory management. So Java did the memory management for you. And then where I work now, Temporal kind of raises that abstraction as well. But in the AI space, we are radically changing the programming model, because now we're programming with natural language. And eventually that turns into code that eventually gets all the way down to assembly language and is running on a processor. One of the interesting things, though, is that in those other abstractions where we had a formal programming language, we had ways, and I studied programming languages in grad school for a while, and to a large extent, that's hardcore math.
Yeah.
Because you're proving these programming languages and the compiler's correct and complete. So you can express everything you want to express. That's the completeness side. And then there's the correctness side of, well, when I write this line of code, it is going to translate into the right assembly language down under the covers. I think this big transformation that we have going into the AI space, where we're now programming with natural language, that's not a formal language. It's not deterministic. It's not an abstraction that is deterministic down to the next level of granular, the next level of abstraction. And so that changes everything. So we have to figure out what the programming model is for this.
Well, I remember when we were first starting to do like text to SQL, and I had a little bit of a gripe with it, because it was like, but why would you want to do that? It's so fuzzy. Language itself is really hard to interpret. And if I want something to happen, there's so many different words that I can use to express just a fairly simple idea.
Yep.
It feels like it's going to be easier if you just use the bound language that we've already created. But I was proven wildly wrong.
Yep.
That is not correct. I do not feel that same way now. I have changed my mind completely, because anybody who has vibe coded or just tried to use coding agents, they go, well, this is very good, right? So it's different now. We don't have that.
It is different, and we also know about hallucinations, right?
Mm-hmm.
So it is different. You're right. It does a pretty good job interpreting. The models have gotten really good at interpreting that. And then, of course, depending on the way that you use them iteratively and you converge on something, and hopefully you're paying attention to what it's doing and that it isn't totally hallucinating something completely wacky. But we're seeing plenty of cases where it is.
Yeah.
And so that's my concern as somebody who studied formal languages. English is not a formal language. And so what are we going to do as an industry to show that? And I think we have to find other ways of compensating for that. I don't think that we're going to get it to the point where it is as rigorous as the math that we did under the covers with programming languages before.
But does
so
it
now
need
we have
to be? I guess that's the big question.
I don't think so.
Yeah.
The mathematician in me is like that was the kind of initial like AI skeptic, like, oh my gosh, like I am so used to deterministic code. I'm happy in that space.
Uh-huh.
I'm happy with the fact that 1 + 1 is always equal to 2, that type of thing. And now it's probabilistic. 1 + 1 might be 3. And so I think what we're going to figure out is we're going to figure out different ways of compensating for it.
Uh-huh.
And so we have to build safety nets. So this is the way things are working. There is a certain level of non-determinism. So how do you deal with that non-determinism? What type of safety net do you have when the translation from this higher level abstraction down to the concrete thing goes haywire?
Yeah.
How do you compensate for that?
Well, in one way, you could look at the idea of durable execution as one of those safety nets, right?
Absolutely. And so that's why, so durable execution, as you know, durable execution is pre-Gen AI craze.
Mm-hmm.
So the company that I work for, Temporal, Temporal, the open source project, has been around for 6.5 years or something like that. And it definitely represents this higher level abstraction. Now, it still falls into that category until you start using it in the AI space. It falls in that category of it's deterministic.
Mm-hmm.
It is, we know exactly how this is going to map from the way that you write and the programming model. So just to very quickly describe the programming model there is that as developers for the last more than 30 years, remember we talked about the physical processor before, right? Developers in the last, up until very recently, have had to understand not the physical processor, but they had to understand the notion of a process.
Yeah.
Like my code is running in a process. As we went into the cloud, in cloud native, we had multiple processes. So we had to start figuring out how multiple processes would communicate, and what happens when the network goes down, and all of those types of things. But we as developers had to think about those infrastructure abstractions. I had to think about a process. I had to think about the network. And what Temporal does is it moves that level of abstraction higher, and it says, no, you as a developer, you get to think about a process as a logical process. We'll map it down to physical processes for you.
Mm.
That's what durable execution does. And so what it says is you get to think about the logical process. We will ensure that we give you durability underneath that abstraction so that as the infrastructure is doing all sorts of chaotic, weird things, we will compensate for all those weird things. You just get to think about this logical process. That's fundamentally what durable execution is. So it is that level. And now we're layering AI on top of it.
Mm.
So it is kind of a deterministic tier that we can leverage, you're right, as kind of a safety, part of the safety net that's going to allow us to compensate for that.
I'm sure you've heard a lot of the chaos monkey or chaos engineering. This in a way is that, but having folks not even worry about chaos engineering because you're going to be doing the chaos on your side and making
we
sure
compensate for the chaos. Yeah, exactly.
I didn't think about that before, but it makes a lot of sense.
Yeah, it's really interesting. So I spent a lot of time, I was around when we moved over into container architectures. So I worked on Cloud Foundry. And Cloud Foundry was the technology that was self-healing before Kubernetes came along. And it had containers under the covers. And so you could deploy multiple instances of an app. And if the container went away, we just brought it back. And I worked with sometimes users and customers who said, yeah, my developers would come in and say, I saw a dashboard that said the container went away. What are we going to do about that? And the people who understood that technology were like, does it matter? Is your app still running? And they're like, Yeah, I guess it is. So maybe it doesn't matter anymore that the container went away.
Yeah.
It's that same concept.
Okay. So then going back to the original idea of, hey, durable execution is a way to almost make up for the fact that we're now communicating with our machines in natural language. There feels like there's other ways that we're making up for it too. I guess one way is MCP.
Yep.
And then other ways are, I'm sure, like, if I really think about it right now, there's probably plenty of ways that guardrails, putting those into place. Other ones that maybe I'm not able to think about.
Yeah, I mean, I love that you bring up MCP because when we start thinking about the way that applications are being written, these AI applications, we've got the agents, right? They're running their agentic loop. And so part of the programming model there is we've got these agents running an agentic loop and they're going to use tools. Tools is one of the first class abstractions in the AI space, right? Even LLMs, even if you're not running an agent, an LLM has tools as an abstraction. You also called out guardrails, those types of things. And so now we've got these tools, there's an abstraction, and durable execution plays across that entire gambit. And so, for example, if you have a long-running agent that might be running for 5 minutes or 10 minutes or 5 hours or 5 days, you want some durability around that. Remember, we talked about how durable execution says, well, you could think about a logical process. So in that case, my logical process is my agent. And the fact that it's going to run for 5 days, it's a logical process. I don't have to worry about what happens with the infrastructure over those 5 days because Temporal will compensate for it. Well, that same durability is valuable when you think about the tools. So are the tools going to be long running? And increasingly they are, because increasingly tools are themselves agents.
Yeah.
So they're going to be long running. So we want to apply durability in the agents. We want to apply durability in MCP, which is why we refer to it as the concept as durable MCP.
Yeah, let's talk more about durable MCP because you mentioned that it's now almost becoming first-class citizen.
It is. So prior to November, so the first kind of early versions of the MCP spec didn't say anything about durability. And in fact, they were mostly request response. So their whole, and that's pretty natural. Like I grew up in like the microservices era as well. And initially our microservices were all request response. And I like to say that the poster children of microservices in that era was Netflix. And they built a whole bunch of services around the request response protocol. So they had things like retry libraries, they had service discovery, they had circuit breakers to keep you from DDoSing things. So it's completely natural to start with request response because it's kind of a natural way of us programming and like our mental model around these things. But in November, they released something called a task, which doesn't change. It's not a new concept. It's still the core thing with MCP is, of course, you've got resources and prompts, but those aren't used a whole lot. It's mainly the tools, right? That's the main thing that's used out of MCP. Tasks don't add a new it doesn't add a new resource. It says a tool can be request response or it can be async. So it can be long running. You fire off a tool, you make a tool call, and you don't expect a response right away. It's not request response. You're waiting, and you're maybe it's fire and forget.
Yeah.
And the cool thing so on the one hand, they could have just defined that protocol and said, instead of doing a request and getting back a result, you do a request, you get back a handle. Now you can interact with that handle by asking for status, getting a result when you get back a status that says, okay, you're done now, you can get back a result. That's kind of, okay, that's great. But the first line in the specification says tasks are durable, which is wicked cool because it's this recognition that tools run for a long time and that if something goes wrong, you don't want to have to start all over again.
You don't want to send the request again.
You don't want to have to start. Exactly. Send the request again. Imagine that you've burned through millions or billions of tokens and then something goes wrong when you're 90% complete. You don't want to have to start that over again. And so the tasks, them being durable, the requirement is that they're durable. That's the thing that changes a lot.
Because you can guarantee that it's going to come back.
Yeah, exactly. So by being durable, what that means is that the client that just connected with the MCP server to invoke that tool, the client could go away, the network could go away, and in fact, the tool itself could go down. Remember, we were talking about durable execution. Says, think of your process as logical. It's always, once you start it, it lives. It just lives. Infrastructure can come and go. All sorts of things can happen. So the MCP server itself can go down, but the specification says tasks are required to be durable. So that means that not everything is lost.
So you mentioned before these long-running agents, and you're also talking about tasks. It feels like that is very much long-running type of use case. What are being done with these long-running agents? Like, what are you seeing out there that needs such long-running agents?
Yeah, so there's quite a number of different use cases. There's some of the same batch type of use cases that we've done all along. So, tools don't have to be themselves be AI applications. It could be, I'm going to go off and do an analysis. I was in a session earlier today that was given by a couple of folks in Amazon, and they were with Prime Video. And they had just a fantastic use case that they talked about where they said it used to be that we did analysis on the streaming, the quality of the streaming, only for the premiere events, for the events where there were millions or tens of millions of viewers, because humans were involved in that analysis. Well, they've now created agents that can do that analysis, and so they're not constrained by human bandwidth anymore. So they created agents, and so now they're doing that same kind of streaming analysis on tiny little niche things.
All the videos.
But that's all long running, because what they're doing is they're crunching through a lot of data. So you were asking about use cases, data analytics, data analysis. Now, in that particular case, they are using an agent to do that. But there's a lot of use cases even that are pre-agent that are just long running. Another thing that makes things long running is as soon as you have some type of human in the loop, humans are bottlenecks, right? So you could be part of the way through processing some tool, and now all of a sudden the tool, the MCP server, the tool says, oh, I need some human input. And now you've got to wait for the human to come back. Well, that might be days. But the process, let's say it's 50% of the way through, and now it's waiting for the human. You want that process to be durable. And so that when the human finally does, and you don't not only want it to be durable, you want it to be efficient. You don't want to hold that in memory for 5 days while you're waiting for the human. So you want to make sure that your infrastructure is being used efficiently as well. And that's not a requirement of durability, but it is a requirement of a really good durable execution platform.
Yeah, and just resource management.
Exactly.
So can we go back to this Netflix the Amazon Prime example? Amazon's not going to be happy we're comparing. I mean, same streaming example. It's long running because the whole time that they are streaming it, I assume they're constantly streaming it. And so they're just taking snippets of time.
I don't actually know the details of the implementation. I think it could be a continual process, which I think is a super interesting use case, which is just it's like an ambient agent. It's always watching and it's always responding. I don't know for sure whether that's what they were referring to or whether they were saying we're always collecting data from the number of times that it has streamed, and then they do it in a batch situation. I don't know for sure. We were asking about use cases for tasks. One of the interesting things about the MCP tasks is that it is largely about batch. So it is not, it does support a human in the loop, but the human in the loop is triggered by the MCP tool itself. It is not one of those things where the MCP tool is doing its thing. It gives you some interim result, and then the external agent is making the decision on the human in the loop and progressing it. It is pretty much hey, we've defined this long-running process. Again, it could be an agent, but now it's the tool that's in charge. The tool is the main player there, which surprises me because I come from a world where long-running processes can be interacted with from the outside,
Yeah.
but there is no, without getting into all of the details of the protocol, the task protocol allows you to create a task, it allows you to get status on the task, it allows you to cancel the task, and it allows you to get the result. It does not allow you to essentially put into there. Like you can't from the outside say, hey, here's some more information.
Oh.
The tool can say, hey, I need more information, and it'll come out to the client and say, hey, I need this more information, but the client can't offer additional information. So I was actually quite surprised about that because I thought, oh, tasks. I thought they were going to be like, we do that in Temporal, but it's a little bit more constrained. There's lots of use cases where you send it over the tool and now the tool is in control, like these batch processes that we talked about. But it doesn't have a protocol. These are some of the things that I'm definitely going to be trying to influence. The protocol's only experimental right now, so there's an opportunity to influence it.
That ability
I would
to
want the
throw
ability
more on its plate.
Yeah. Yeah. There are ways of doing it, but it's a little bit odd. You have to define other tools with the same server, and that might be a best practice. I haven't quite gotten that far yet. We'll see.
Can you break down, I'm still trying to wrap my head around the tasks and the different use cases. So different batch processes that you've seen being done with tasks?
Yeah. So there might be, for example, it could be like an invoice processing example, which is exactly what I did in my talk, was invoice processing. So you're going to submit an invoice. You've got a tool that is an invoice processor. For the most part, you submit the invoice, and what does it need to do? It needs to do some validation. Then maybe it needs to ask the human for approval. You know, you've got some policy there that says, anything under $500, just go ahead and process it. Anything above that, or if there's some other policy, some weirdness about the invoice, then you have to have a human in the loop. The tool would be the thing that decides. That's where the policy is running. The tool can come out and say, hey, client, I need approval. And then you could be paying parts of that. And maybe the entire invoice doesn't need to be paid at once. Maybe you've got a complex invoice where you say, I'm going to pay this in increments. So that is a long-running tool where, let's say you're going to pay it quarterly. You can model that as a single tool, a single invoice that you're processing. You pay this quarter's, and then the thing goes to sleep, and next quarter it wakes up and it pays the next installment.
Whoa.
So that is what I mean by a long-running thing that you can imagine an agent saying, hey, go ahead and process this batch of invoices for me. And that's the process that's going on in the background.
And that's where you talk about the resource management is important, because you don't want it for a whole month to be there thinking about that. You want it to go to sleep.
Exactly.
Huh.
Exactly.
And so, yeah, scale to zero is important here on these tasks.
That's right.
And then you're thinking, wow, wouldn't it be great if I could add more invoices to that while it's happening instead of having to kick off a new task with new extra invoices? Is that kind of the idea with the...
I think there's a number of different ways to do it. The way that I did it very, very naively in the beginning is that each invoice was its own task. You can also imagine batching those things and saying, actually, a batch of invoices is a task. And within that, you can break it down into, subtasks, or because each one might have its own schedule. So there might be an invoice that is paid quarterly and another one that's paid weekly, and those types of things. And so going back to the durability conversation that we've been having all along, you're right. It needs to scale to zero. And remember, I said the infrastructure can go away. So where does that timer live? The timer has to survive that infrastructure failure as well. And so we like to call those things durable timers. And so we have this notion of like timers need to be durable. Human in the loop needs to be durable. The compute needs to be durable. All of those things. So durability isn't just retries or state management. It's a whole complex set of things. And that's what I mean by programming language, right? Is like, here's this new abstraction of durability that you can apply across a bunch of different programming elements. And as soon as you have the notion of a durable timer, then you no longer have to program that.
Yeah.
So
Yeah, you have to keep the time though, because otherwise, when is it going to know when to wake up?
that's what, for example, Temporal has durable timers,
Yeah.
and they live in the Temporal server, so it knows when to wake up. Your process can go away. That's what allows us to be efficient with that, is the processes go away, the timer fires, and now a worker process that's always checking to see is there anything new is like, oh, I see this timer fired. Oh, that timer corresponds to this thing that's asleep over here. I'll wake it up now.
Yeah, and so I'm starting to get a better picture, and in my head, I'm kind of envisioning it as like different things happening that are creating chain reactions, and you have to make sure that each one of those things is working, because if you have some kind of a problem, then the domino is not going to go to the next domino, and so everything has to be durable.
Yes.
That's why I'm understanding the idea of, okay, durable execution doesn't mean just durable execution. It means durable timers, durable compute, all of that.
Exactly.
Huh.
Yep.
Okay. So that's tasks, and a little bit of like MCP being more durable and bringing that to its own DNA in a way. Hopefully we see more of it, and so that most things are durable. Is there ever times where you wouldn't necessarily need like durable execution is overkill?
Oh, definitely. I think that there are some places where the cost of recomputing something is so small that you don't necessarily need to take on that burden, because what we're essentially doing is we're pushing some concerns that used to be application concerns down into the infrastructure. That's what we're effectively doing. Of course, that means your infrastructure is a little bit more complex. So like I said, short running things where the cost to recompute that over again is very, very small. Other things are things like embedded systems. So if you aren't necessarily running a distributed system, so you're not deploying your application out into the cloud and have multiple instances, embedded on, like, let's say a car, for example, probably not needed there, in part because everything's different there. You're doing embedded systems, you're probably programming in C and C++ and those types of things. You're still doing your own memory management because things need to happen really quickly. You're operating at a level where you're still operating at that lower level of abstraction. So there's a number of those things. But one of the things with durable execution is we've seen this with some of our, the early adopters of durable execution, is that they come in and they adopt it for a use case. And once they understand this new programming model, all of a sudden they're like, they can't see problems.
You can't unsee it.
They can't unsee it. Now they want everything to be built that way. And we hear stories. One of our most vocal champions is from Yum Brands, Matt McDowell. And he tells this great story of product manager came to them. They had been talking about a feature for a while, and they had estimated that it would take weeks or months to implement. And the reason it was going to take that long was because it was this highly distributed application where, like we talked about earlier, the developers were going to have to worry about all these, like, okay, I've got this process over here, that might go away, so I have to make sure to store some state over here, and I need a message bus over here. And it was just a complicated topology and a complicated, like, workflow that they needed to wire together themselves. A little bit of a Rube Goldberg machine that they had to build. And Rube Goldberg machines, metaphorically, are really hard. They're hard to operate. And when they rethought about it in this model where they're like, well, if I think about it in terms of a process that doesn't go away, something else is taking care of that resilience, they were able to implement it in a couple of days. Like, that's the power of a different programming model. Like, we couldn't build AI systems in assembly anymore. We just couldn't do it.
So this developer couldn't unsee it because there was such complex topology, but he was able to say, let's imagine that these are always there. Like, we can take them for granted. Yep. And so now, if we are able to take this for granted, that it's going to be there, we don't have to make it as complex as we thought we did.
Exactly.
But I guess where's that parallel, or where's the I'm not drawing the conclusion of, okay, if it's always there, then it's less complexity.
Because the complexity is moved down. The higher level abstraction is they get to deal with this abstraction that makes it less complex for them. And what we do in temporals, we map it down. It's complex. The runtime topology is just as complex. It's that the developer doesn't have to wire all that up themselves and create all of those components themselves.
I see.
Temporal does that. So one of the things that I like to say is that event-driven systems and event-sourced systems, which is an added complexity on top of event-driven systems, it's an incredibly powerful paradigm that we need for runtime resilience. But it's so hard for humans and non-human coders to understand, because there's so many moving parts, and each one of those is a little bit different. It is truly a Rube Goldberg machine. They're all a little bit different, and like you said, dominoes falling on dominoes. And so that's another one of the things. I've not done any like tests of it, but I am, being somebody who uses coding agents, if you give a coding agent a simpler programming model, they're going to do a better job writing the code in that simpler programming model as well. So the simpler programming model up until recently was a huge benefit for our early adopters. And we have a few 100,000 people are using Temporal. Which is still small compared to, I think it should be in every developer's toolbox and will be in a few years. But it is now, I think the even bigger thing is like coding agents wouldn't do a very good job writing some complex thing in assembly. You give them higher level abstractions so that the LLMs can reason through that. And so that's another thing with durable execution and that change in programming model, is that we give that programming model, the understanding of that programming model, to the agents, and then they can write that code better as well.
And how does it work if I now have all of this very complex topology and I install Temporal? I have to have Temporal map everything and then almost give a guarantee that, all right, we're going to secure this, or we're going to durabify this.
So it's actually that Temporal brings that complex topology. So Temporal brings the messaging substrate. Temporal brings things like durable timers and stuff. So it is that the developer gets to write in this abstraction, and when they deploy those applications, Temporal takes what looks like a single process application, because it is logically a single process, and it maps it down to that complex topology. So it's not that the developer has to think about the complex topology. Temporal basically does that for them.
So that developer that you were saying, Matt was his name?
Matt McDowell, yeah.
He had to worry about everything in his former life, where he's looking at it and he's trying to map out story points and saying, this is going to take 6 months. And then he says, oh no, well, maybe we'll just hit Temporal instead. And then you are in the background bringing all of that he thought he was having to wire up.
Exactly.
And so in a way, you're sitting in between his system and that complexity in the system, and he's just interfacing with you. And now everything's making sense. It took me a minute, but yeah, I'm getting it while you're like, yeah, that's a higher level abstraction. That's it's what we've been talking about.
Yeah, and Demetrius, that is that aha moment. Brilliant that you had it. It takes a while because we have spent, like I said, decades thinking about building systems with these lower level abstractions. Even as our programming languages gave us higher level abstractions, we fundamentally still had to understand the architecture of the computer and the architecture of the network and things like that. What I'm saying is you don't have to anymore. Yeah.
Just like you don't have to learn TypeScript or Python anymore.
Yep.
It's
Absolutely.
good if you know it and you can debug through it, but it's also, you can also create a lot of stuff without knowing it.
Yep, that's right.
So, yeah. All right. Well, that kind of drives it home and brings me full circle to, okay, we started this conversation with the evolution and the thread that has been going on these abstractions and programming models and recognizing how we're just continuously moving up and up and up, and how durable execution is bringing a new level of abstraction to this, just like we have natural language bringing a new level of abstraction to the way that we're interacting.
Yep, exactly. And I think that probably the way of layering it is that we've had these traditional programming languages, temporal layers and abstraction on top of that, which is durable execution. That's what allows temporal to like figure out abstract away the physical processes and network connections and all of that stuff. We handle that for you. And then AI, the natural language programming sits over the top of that. So
because temporal isn't a language per se, it's more of just like a helper.
I refer to it as a programming model. Our SDKs are in a bunch of different languages. We're not giving you a new programming language, but what we are doing is we're giving you a new set of abstractions, so a new programming model, where instead of you deciding, oh, here's a process boundary, you basically break up your code into the things where things could go wrong. Like, I'm going to make a network call here, or I'm going to go down to a database, or maybe it's a long-running thing where you don't want to have to recompute it if something goes wrong. You put those things into activities. That's one of our primary abstractions. And then you wire the activities together in what we call workflows. And so that's the new programming model. And it takes a while to it's so fundamentally different that it takes a while to kind of do that mindset shift.
Yeah.
So I had something similar where I did my undergraduate in the greater LA area, state school, learned all sorts of programming languages. They were really focused on getting you ready for industry. So it was learned half a dozen different programming languages. And then I worked for a few years, and then I decided to go back to grad school, and I went to Indiana University, which is a research university in southern Indiana. Programming languages is their thing. So that's really where I got hardcore into programming models. Well, because they're more research oriented, the first language that they teach their students as undergraduates is Scheme. And you could always tell the students who came in as freshmen who had already programmed in iterative programming languages like Pascal and Fortran and C and those types of things, because they had a hard time shifting their mindset over to a functional model. Very similar with temporal is that, but once you make that shift, then you're like, oh, that's a different programming model. I can do totally different things with that now.
It enables you.
Yeah.
Well, that's a perfect place to finish it. Thank you for doing this with me.
Thank you. It's been so fun.